Hello everyone, my name is Jay. I'm a fifth-year PhD candidate at the Department of Chemistry, U of A. Today I'll be presenting my work titled Hollow Mesoporous Carbon Nanospheres Decorated with Metal Oxide Nanoparticles as Efficient and Earth-Abundant Zinc-air Battery Catalysts. Based on projections, by 2050, the renewable energy production globally will at least double. Despite their sustainability and environmentally friendliness, they still suffer from their intrinsic intermittency. This essentially creates an imbalance between the energy supply and demand on the grid. To solve this problem, an efficient and cost-effective energy storage technology is an urgent need for us to fully utilize the benefits and full potential of renewable energies. This brings us to zinc-air batteries. Zinc-air batteries have multiple advantages. First of all, zinc-air batteries have significantly higher specific energy than our current lithium-ion battery technology. Secondly, zinc-air batteries utilize aqueous electrolyte. This essentially eliminates the risk of catching on fire or explosion. Finally, zinc-air batteries have much lower raw material costs in comparison to lithium-based battery technology. The way a zinc-air battery works is when the battery is discharging, the zinc electrode reacts with the hydroxide anions from the electrolyte to form zincate anions and electrons. These electrons travel through the external circuit to the air electrode, where the oxygen from air is being reduced into hydroxide anions. This process is commonly referred to as oxygen reduction reaction, or ORR. When the batteries are being recharged, the reverse reactions occur. The reverse reaction for ORR is called oxygen evolution reaction, or OER in short. Unfortunately, like Matt just mentioned, both OR and OER are kinetically sluggish. In other words, they both require electrochemical catalysts for the battery to function efficiently. The conventional OR catalyst is platinum, and the OER catalyst is ruthenium dioxide. Both materials are extremely scarce and expensive, which essentially hinders the potential large-scale commercialization for zinc-air batteries. This brings us to my research. My research focuses on developing a hybrid between carbon nanomaterials and transition metal oxide nanoparticles to synthesize this precious metal-free and efficient zinc-air battery catalyst. In this work, we utilize nitrogen-doped hollow mesoporous carbon nanospheres, or HMC in short, and we decorate them using various combinations of metal oxide nanoparticles. Based on this electron microscopy images, we can see that not only is the exterior surface of the HMCs were decorated with the metal oxide nanoparticles, so was the interior surfaces. Based on this elemental mapping, we can see that the expected elements for each corresponding mixed metal oxide decorated HMCs were overlapping. Moreover, they also overlap with the dark field transmission electron microscopy images on the left-hand side. This is the indication that the nanoparticles we observed in those images were indeed the expected transition metal oxide nanoparticles. In terms of performance, the cobalt oxide decorated HMCs and manganese cobalt oxide decorated HMCs exhibited much higher discharge potential than the benchmark 30% platinum and 15% ruthenium dioxide. In terms of charging potential, all three trimetallic oxide decorated HMCs exhibit a much lower charging potential than the benchmark platinum ruthenium. This is an indication that all the hybrids exhibit higher OR and OER catalytic activity than the platinum ruthenium catalyst. Finally, we also evaluated the stability of the hybrid. After over 100 hours of cycling, the cobalt oxide decorated HMC maintained over 56% efficiency. In comparison, the platinum ruthenium benchmark only maintained about 50% of efficiency after just 50 hours of cycling. This is the indication of superior stability of the cobalt oxide decorated HMC. In conclusion, in this work, we have successfully synthesized efficient and cost-effective precious metal-free zinc-air battery catalysts. Finally, I want to thank my boss, Dr. Jonathan Veinot, as well as my major collaborator, Dr. Douglas Ivy, as well as all my group members and all the Ivy group members as well, especially Matt. I also want to thank all the funding agencies. And finally, I want to thank you all for listening.